Welcome to this Arthur Holmes Medal Lecture. It's a real pleasure, and I actually feel it like a privilege to be allowed to introduce today's speaker, Celâl Şengör, who has won the Arthur Holmes Medal this year. And the Arthur Holmes Medal is one of the 3 union medals of the EDU, and when to be awarded this means also that Celâl now is an honorary member of the EDU. And I will not say very much. You have come to listen to Celâl, but I will just introduce you to the objective of the Arthur Holmes Medal. And obviously, the highest award you can receive from the EDU carries with it that he has been excellent in his science. He has achieved an exceptional international standing in solid earth geosciences, defined in its widest sense. And everyone, I suppose I don't need to introduce who Celâl is. You all know him for his outstanding contributions to geology, tectonics, and so on. So I'll just read the citation for the medal. So the 2018 Arthur Holmes Medal and honorary membership is awarded to A.M. Celâl Şengör in recognition of outstanding contributions to tectonics and paleogeography, which have fundamentally changed our view on Earth's history and the understanding of geological processes. And with these words, I would ask Celâl to come up on stage and present his talk.
Should we look very formal in front of me? Thank you. Thank you, Hans. Ladies and gentlemen, it is an enormous honor to be here. Winning medals shows that you have important friends in important places. Winning the Arthur Holmes Medal of the European Geoscience Union is a very special honor because our science was born in Europe. Europe, whether we like it or not, is the place where human civilization, as we call it, civilization originated. It originated with the Greeks. And we are all inheritors of that fantastic tradition. And I hope we can keep it. And when I look at all of you here, I am so filled with not only honor, but also with hope that I think we're doing fine. I was asked to talk about whatever I like today, as the winner of the medal, one of the privileges that comes. And I remembered one thing that my late friend and Professor Kevin Burke said: when you give a talk, if you don't annoy at least one person in the audience, that talk is wasted. So I'm planning to annoy half of you. And the source of the annoyance will be that I will tell you that geology, the way I learned to do it, is fading, and that it represents a great danger for our sciences, for the sciences of the earth. And I will try to impress upon you the merit of geology as it is done with a hammer, with a pencil, with a topographic map, with a magnifying glass, and a good pair of legs, and of course, a good brain. that is something you can't do without. So, if I can start with the next slide, I don't know how to do it. Yes, are you going to do it for me? Yeah, I use the hammer, yeah, that's right, yes. You see, Hans is right. I'm going to start the theme that I have chosen. This one, right. Oh, this is the gentleman after whom the medal was named. And something that he wrote later in his life about an event that happened to him when he was in high school is the main theme of my talk. So next slide, please. When Lord Kelvin's compression of the duration of the Earth history between 20 and 40 million years caused universal consternation among geologists at the end of the 19th and the beginning of the 20th century, because he was such a great physicist and that he had mathematics at his command. And geologists said, yeah, he's wonderful, but what is this? It's bullshit. Well, but how do we prove it? So when Arthur Holmes was in the last form in high school, he was interested in geology. And when he heard what Lord Kelvin published, he was despondent. And his physics teacher, and Arthur Holmes says he was a brilliant physics teacher, this is Mr. Mackintosh. Mr. Mackintosh said, look, boy, here is Edward Seuss's first volume, The Face of the Earth. Read it as a consolation. He said, that's the truth. This is the theme I want to emphasize. Next slide is a little show in German as to what a geologist does. Okay, Hagar asked, was will ich eigentlich? What do I want really? And he says, was will jede Geologe? What does any geologist want? And he says, ich brauche nicht viel, I don't need much. Einen Freund, mein Hammer. A friend, my hammer. Einen Traum, a dream, ein Aufschluss, an outcrop. Eine Liebe, das Handstück. A love, which is the sample, hand sample. And ein Ziel, and a target, an aim. Verständnis der Erde und ihrer Vergangenheit. Understanding of the earth and its history. Next, please. Well, you know about Karl Schwitzweger, was a German romantic painter. He painted geologists as a fairly thick fellow. Doesn't exude intelligence when you look at him. Okay. And this was the general understanding in the 19th century. The geologist was a collector. And the next slide will show you a mineralogist. The mineralogist didn't fare any better. So, what I'm going to tell you is, how do we start? And I'm going to start in a very mundane way. Next slide. Well, what do geologists look like in the field? Okay, well, in the old days, they looked like this. They were gentlemen. They went out to the field in frock suits. This is Robert Broom in South Africa, looking out for vertebrate fossils. This is one of my students, enjoying his field geology. So there were certain changes in emphasis. Next, this is the new hammer. Geologists use things like that. I didn't dare bring you any of the geophysical instruments. They're huge, some of them. But this is the sort of thing that now goes for good research. And if you work in a place like that, publications are guaranteed. And funding is guaranteed. But next slide. You see, this is how we had started. We wanted to know the structure of the Earth. And here is a cross-section from the atlas that Bromme had published for Alexander von Humboldt's Cosmos. And this shows at least his understanding of the crust of the Earth. Well, I mean, you're going to say this is all nonsense. Of course it's nonsense, but it was a step towards understanding. It was something that you could criticize by going to the field, mapping it, and showing that it's not like that, but this is how it is. And when you say this is how it is, you know that what you say is also wrong, but doesn't matter, as long as it is testable. Next slide. Now this is, ladies and gentlemen, I don't know how familiar you are with these cross-sections. These are by Émile Argan, a gentleman who spoke 17 languages fluently. And when Argan, as a PhD student, sorted out the structure of the Alps, he had nothing but a hammer and a pencil and a map and a magnifying glass. Because he realized the axial plunge from the Ticino Dome westwards lay bare the internal bowels of the Alps. And he said, this is what it looks like. And Albert Heim, in his famous Geologie der Schweiz, says, Argan has sorted this out with a memory and imagination that escaped me. He said. He just couldn't understand how a person could grasp this complication and express it so simply. And you know that the Swiss have published, not too long ago, a wonderful atlas of geophysical data showing at depth the structure of the Alps. Next slide, please. Here it is. That's the structure of the Alps today. That's the structure of the Alps that Argan had published in 1924, actually in 1916. But this also shows the Austro-Alpine maps on top, this is from La Tectonique de l'Asie. You can see that we really haven't improved all that much on him. The details, yes, but not the principle. Because the way he did it, because he looked at the temporal and geometrical relationships of rock bodies on Earth. That's how you understand the architecture of this planet. And that's how you deduce from it, using the fossils it has, using the minerals it has, its history. And, ladies and gentlemen, we are historians. Let's forget that. We are historians of nature. And history in original Greek doesn't mean study of the past. It means investigation, which includes the past. Let's go to the next one. Now, a humble thing that I have done myself. There are some friends sitting in the audience, one is right in front of me, who know this place, Albula Pass. Oh, that's why Wolf Christian Dullo is laughing. When I was sent by John Dewey to the Albula Pass, John said, you're gonna map everything, including glacial deposits. And when I went to the Albula Pass, I was so frightened by the complexity. But then I remembered, okay, what I need to do is to go out, map the rocks. This is the mundane part of my talk. This is something you all know, but we do less and less of this. Look at the complexity, and let's see from what this simple outcrop observations, a complexity like that, where do we go from that? Next one. You undo all of this deformation, you end up with a sequence like that with two normal faults in a tiny place like the Albula Pass. And then the whole thing gets folded. But in the Alps, everybody thinks when you get first folding, it goes to the north. No, it goes to the south. It's a south divergent structure. And look at the normal faults. They couldn't recognize themselves if they saw themselves in the mirror now. Okay, next one. Look at that. Deformation continues. The whole thing separates into two. Okay? And then here, this separation creates little slices. Next one. Look at the slices. Every one of these things you cannot ignore if you want to understand the kinematics, if you want to understand the displacement, and indeed, if you want to understand the physics of how these things have moved. You need to know these details. You can't assume a spherical cow. You need to know the cow. Next. And then, after the whole thing is assembled, the whole thing gets refolded on a huge fold. These are the Großfalten in the Alps. Next. And then you take all these things out, you realize that you're just here. A tiny little place. But this tiny little place gives you a South-Virgin structure. And you say, well, I mean, this is not what we had learned in school. Why is this South-Virgin? This leads you to the structure, Hercynian structure, of the basement of the Southern Alps. This leads you to the fabric of the Hercynian. Next slide. Okay, and then you realize how, because of the normal faulting that in the Triassic and Jurassic opened the Neotethys, that these normal faults had directed, but not individually localized, the big thrusts that go north. The whole thing has been completely redeformed. Look at that. They have been completely redeformed. And you can't pass over these things as mere details, because they are part of the history. Next. Let's go to another planet, Mercury. I asked my good friend Sean Solomon, when the Messenger mission started sending radar pictures, I said, I would like to receive some of them, because I was curious as to what a planet that contracts thermally actually looks like. Because this is what we used to think about the Earth, and we now know it's not. But what does a contracting planet look like? Sean said, no, let's do it that way, he said. You come over. As a 2E fellow, we'll pay all your expenses. You stay 2 weeks. You'll look at all the images. I said, oh, what a good idea. So I went there, and to my amazement, ladies and gentlemen, we started seeing structures, thrust faults, orogenic belts. Next one. The blues are structures of shortening. They are folds and thrusts. You look at the literature, you'll read things like wrinkle ridges. I mean, we're not talking about a piece of cloth in a, dish basin. What is a wrinkle ridge? It's something silly. It's an expression of I don't know and I don't care. So I told Sean, I said, look, Sean, I said, geology has names for these structures. Why don't we use them? Previous publications had detected 16 structures of shortening origin, and the geologists told the geophysicists that they could give them a shortening of about 600 meters, radial shortening. And the geophysicists said, no, can't do, we need 10 kilometers. And the geologists said, no, you can't do that. And when we started working on Mercury, as opposed to 16, ladies and gentlemen, we found 5,900 of these structures. Because it requires extensive field experience of geology. You have to recognize these structures. You have to know their siblings on Earth. And when this was done, we've come up with a shortening a bit more than the geophysicists required. Next one, please. Because there is no erosion on Mercury, you can use fold geometries to infer thrusts. From these, you can get shortening amounts. They far exceed anything that's ever been calculated on Mercury. And anybody who has studied the writings of August Buxtorf of Basel, when he mapped the Jura Mountains and discovered the Abscherung, the décollement, and the fold style, you don't need any newer literature to recognize this. That's why I always say, you want to do tectonics, by God, you work in the Alps. If you haven't licked any alpine rocks, you're up shit creek. You have to know the Alps. The only reason is because they've been studied in such excruciating detail by so many generations and by so many rival schools. Austrians hated the Swiss hated the French, and the French hated the Italians. And this mutual hatred was extremely helpful. And the Dutch descended from the north, worked on the southern Alps, and everybody hated them. But it was wonderful, the things we've learned as a result of all these controversies. See, that's why things like that come easy to the field geologist with good experience. Next one. Okay, now this is the structure of Mercury. And here you have these deep-seated structures. And there you have these shallow structures, décollement structures, that are creating the folds and thrusts. And I said, well, why don't we use Stiller's old term of Germanotype and Alpinotype tectonic? I mean, these are concepts that have been invented in central Germany, proved unbelievably useful. Stiller used them for the Rocky Mountains. I said, why don't we use them? People know when we publish these things. Of course, the older people do, not the younger people, because they don't read the old literature. Next one. Now, these are the structures that you see on Mercury, on Venus too. And these structures, ladies and gentlemen, were recognized at the end of the 19th century by Zeus. These are all from Das Antlitz der Erde. If you know these structures, then you suddenly realize that Zeus had sorted out the geology of the Earth. He knew the continents. He didn't know the oceans. He knew the continents. In the continents, no structure that he interpreted turned to be grossly wrong. Not one. That is an amazing lesson. Next. This is Mercury. Again, this is the extensional phase, and we called it the de la Métrie phase. Already in 1775, de la Métrie said, if you have a planet start contracting, the first thing that will happen, it's going to produce cracks in the surface. And then, as it cools, the upper layers will start shortening, and the lower layers will extend. This is what we see on Mercury, these huge basaltic flows early on in the planet's history. Then they get folded. Again, this is done only by looking at the geology in essentially air photos. I mean, these are radar pictures, yes, but you interpret them like air photos. Next. Now we come to a recent paper by my good friend Phil England and Greg Hausman and Nake. They have beautifully looked at, well, they have beautifully mapped a rather nice data set. That is the GPS measurements in Turkey, and you can see Turkey is speeding beautifully westward, and it's moving, and they said, this is so easy to explain if you know physics. Which is indeed wonderful. It'll be so simple. Next. They said, here it is. There is the smoothed topography, and this is the gravitational potential energy. I said, you can see that this high area is inevitably going to push Turkey. And if you use a thin sheet analogy, you'll see how it spreads out. Okay? This paper was much lauded by my geophysicist friends. And I said, it really is beautiful. I wish it were true. Because, ladies and gentlemen, Chronos intervenes. Time. Now, this is Turkey about 11 million years ago, late Serravallian. Turkey had started moving west. We know that. It's all been dated. The faults are known. How it's moving is known. How it's falling apart is known. But the tragedy of it is, it was moving from an area that was underwater, that was under the sea, towards an area that was 3 kilometers high. Well, if you really had that thin sheet analogy, it would move the other way. It doesn't. So, when you look at this, you remember Walter Elsässer. Walter Elsässer told us about, in geophysics, about boundary forces. And you ask yourself, are these things stronger than we think? Next slide. Well, Turkey rose in the east, okay, but we do know one thing about its consequences. Next, we have all these basins along the North Anatolian Fault. They're wonderful because, as you can see in these very boring-looking stratigraphic sections, they give us timing. When do these basins get going? They tell us when the fault starts moving. So, next, not only do they tell us when this fault starts moving and how it progresses, it further tells us that it speeds up with time. Next, these are the cross-sections. Every one of these basins, you have to know the geology to be able to interpret it, what they are. Are they wedge basins? Are they pull-apart basins? Are they sag ponds? Every one of these have a different kinematic interpretation. All of these things you have to map and interpret. Next slide. The same thing we've done the bottom of the Sea of Marmara. The 1999 earthquakes in Turkey killed about 40,000 people. Well, they were immensely useful, not because they killed people, but because they enabled us to start campaigns in the sea, particularly under the leadership of Xavier Le Pichon. Xavier got so excited about the earthquake and the fact that the fault was going right underwater, and himself being a marine geophysicist, he was jumping up and down with excitement. And he started all these projects, wonderful projects, with French and European Union money. And we now know the geology of Marmara better than any other inland sea. And we can map our basins. We can look at their geometry in a way that we can't do on land. It's too expensive. And we have drills. We can look at the timing. Next. Now, this shows you that the fault started, of course, with zero velocity. Otherwise, you'd get infinite acceleration, which you can't have, right? And then, look, it gradually accelerates and comes to the present day velocity of the fault. Now, some people say, well, you know, the fault started, the fault has a rate of movement so and so, and it has an offset so and so, well, it must have moved in the Zankli. You say, how interesting, because this bloody fault is of different ages and different places. And it has not had the same speed throughout its history. Therefore, please do your geology properly before you say anything about how and when this fault moved. And this shows you the result of years and years of actual mapping, fossil collections, dating. And finally you come up with this picture. And this picture contradicts many of the facile models that have been built on pure physics and mathematics. Next. Look at the courses of the rivers in Anatolia. That's another funny thing. You know, we learned that these rivers come, they get offset at the fault, move on. This is what our textbooks teach us. But they don't do that, do they? I mean, look at the Halis. This is the Kazimir. How it bends. It bends back. You know, also in Iris, which is the Achillean mark, the classical Iris. Look at Euphrates. It looks as if these rivers sense the fault before they get there. Well, how is that possible? That's absurd. Well, it isn't if you map it properly. Next. That's Euphrates. You see, the way it comes into the North Anatolian Fault, it gradually bends. And if you look at these things, these are not pristine areas, they're all faulted. Next slide. This is Iris. Look how Iris makes meanders. But these meanders really don't make much sense in terms of a meandering river. And again, when you map it, you realize every meander corresponds with a fault. Next. So, when you have a river that enters a faulted area, it never encounters a single fault. And you can see, you can build your models in your mind as to how these bends may originate. And you can say, well, if I have panels like that moving parallel with different offsets, with increasing offset towards the principal displacement zone, I might be able to explain that. Next. And this is how perhaps these gentle bends form. And once you do that, you go to the field and you see, are these faults really there? And to your amazement, some are there, some are not. Well, how are you going to explain the ones that are not? Then you realize the pattern of faulting you've imagined is too simple. You have to move on and see how a shear zone develops. Next. Now, the shear zone developed within that weak areas in Turkey. These areas that are indicated in blue are all filled with deep sea muds, serpentinites, knockers of limestone. And these are suture zones that go straight down to the lithosphere. So these are weak zones. And to your amazement, they have localized these faults. And within them, strike-slip tectonics reigns. Next. Now, when you remember what my good friend Phil England and company have done, you see, they have ignored all of that part of Turkey. They have taken everything from here on. Because from here on, it's all right to model. But when you come here, look, the GPS shows that within Arabia, Arabia moves with a certain velocity, and there's a suture in front of it. You would expect that the velocity would drop. Now it doesn't. So Arabia has already incorporated all of that weak area in eastern Turkey, the whole squashy zone. And only when you cross its border to Caucasus, to the Caucasian mountains, does the velocity suddenly drop. And that tells you the deep structure of eastern Turkey. Next slide, please. You know that the same model, the thin sheet analogy, was published by England and Mackenzie in 1982. It was a wonderful model, and it did explain a lot of the GPS today. But look at Asia. Well, Asia is funny, isn't it? It has too many faults that don't appear on your models. And these faults are not bitty faults, they are huge. So something else is going on, perhaps. Next slide. Now, we jump back to 1924. What was going on in Asia? Well, Émile Argan, sitting in Neuchâtel, he gathered all the geological information he could, including expedition reports. He plotted them on an Asia map, and he tried to interpret kinematically how individual pieces of Asia may have moved, and he used Zeus's kinematic indicators, the virgations, the syntaxes, the Kettung, the deflections. And he said, this is what we get. Now, you see all these structures that I've shown you earlier that appear on this map in different places. And Argan made certain assumptions. And these assumptions were, if you have a fold, okay, it probably shortened mostly like that. He said, let's make that assumption. And he came up with this picture. Next, he removed all the structures. He came up with a flow field of Asia. Now, if you have read Zeus's 1898 paper, the Asymmetrie der nördlichen Hemisphäre, and then his Sur la nature des charriages in 1904, you realize Zeus had been playing with this idea of the flow of continents. Argan and Taylor took this idea, they applied it to the entire continental surface, and they said, indeed, the rocks are flowing. And when Argan published this, Nobody understood a word what he was talking about in the 1922 International Geological Congress, because geologists were not used to that. Next slide. On the left, this is the forward velocity field derived from earthquakes and GPS in Asia. Okay, this is Aachen. Now, let us go to where the Dujiangyan, the Sichuan earthquake had happened. There's a prediction of the model on the basis of our current data. When I say current data, data of present-day motion. Look at Aachen. You put a discontinuity right through the Songpan-Kanse system. And who was right? Ladies and gentlemen, Aachen was right. This is extraordinary. This shows you that you just can't take present-day motions and assume that the planet has been deforming using the present-day vectors forever. They change. Why do they change? Because the entire continental lithosphere and the oceanic lithosphere, to a much lesser extent, is inhomogeneous. Because there is a history. Topography changes. Rock characteristics change. You can only know these things by mapping them. Next one. Okay, here is the seismicity of Europe. We have long heard about stable Europe. The only stable place in Europe is Russia. I mean, if you know what I mean. Look at the distribution of the earthquakes. Next slide. This is a map that my colleague, Dr. Nalan Lom, is sitting right here with another younger colleague. They have mapped and dated the faults in Europe. Ladies and gentlemen, when you look at that, you realize that all the earthquake hazard maps that are drawn in Europe are overly optimistic. Because they are drawn using earthquakes. But we know that the earthquakes can have a repeat time in Europe of 1,000 years. They don't show up on our hazard maps. This is what the still active plate boundary zone is in Europe. The plate boundary includes the Mediterranean, of course, but it goes all the way to the Tornquist-Tessera lineament. It enters North Africa, stops at the Atlas Fault. All of this area is dangerous from the viewpoint of earthquakes. In that zone, an earthquake can hit any time and really make your head ache. In Central Asia, same thing happens, but there the earthquake magnitudes go beyond 8, which is really frightening. Next. When you do your geology, you draw your plate boundaries differently. These are the real plate boundaries on Earth. I mean, Seth Stein, a very sensible geophysicist, Seth started thinking about that. And he thought that he invented the term plate boundary zone until I reminded him that Kevin and I had introduced that in 1980 already. He said, oh, I hadn't read that. I said, yeah, of course, because it was published in Journal of Geology. It was a paper on geology of Jamaica, which you wouldn't normally read. Okay. But this is the distribution of high strain on this planet. But in between, the plates also strain, as I just showed you. Next. This is what our geophysicist friends told us when plate tectonics came about. Right? And the geologists were trying to justify that. This was foolish. It was a wonderful thing to know that the Earth is divided into plates. Yeah, but they are the boundaries. And geology could have told us that. And this is Edward Süßes, Das Antlitz der Erde. This is a map I drew from his descriptions using his maps. And here I drew all the trend lines that he had drawn. I didn't infer any trend lines from Süßes descriptions. I drew what he drew. Ladies and gentlemen, it is the most amazing thing. You can't move a line. This man's knowledge of world regional geology was staggering. I mean, Wilhelm Salomon said, that he had an incredible command of the world literature. Not only did he have this command, he used to correspond with these people. I mean, he'd never been to East Africa. He discovered the East African rift valleys without ever being there. That shows you the power of geology. I mean, his analysis of the Altaids, I always say we could not have published that Nature paper that really told us how Central Asia was structured without Zeus's guidance. Next slide. This is the last slide. Here is the man. And these are his instruments. His geological map, his geological hammer, his compass, a letter which he used as a geological instrument. He used to correspond with people like mad, with other geologists using the same instruments. And he left us a legacy that still baffles me. And Argan said in 1922, when he addressed the International Geological Congress, he said, "Mesdames et messieurs, if the master were to return among us, he would touch perhaps a detail of a structure here or account for an episode of deformation differently there, but he said he wouldn't touch the main plan of the edifice because it stays true." And you'd be amazed that after so many years, almost 100 years, what Argan wrote remains true. So that's the merit of geology. It isn't to belittle anything else, but if you do your geology with these simple instruments, you'll go very far. Of course, then you'll go even farther if you talk to your geochemists, geophysicists, friends, etc. But if you don't do this, those friends of yours will get nowhere. That's the basic message I want to convey. Thank you. Thank you. This geophysicist won't let me off the hook.
Yeah, I think one of the key messages here is that we should actually talk more together.
Yes, absolutely. That we are one community, and what happened to geographers should not happen to us. That's really important.
So, Celâl accepts to take questions. Are there any or comments?
Oh, you can't be that gullible.
So now you're spoiling his mood because he said at the start that there must be someone annoyed.
Yes. Half of you, I hoped. No. Bilal, you don't count. You're one of us.
Do you want to?
No.
Okay, there's a microphone here.
Where?
Over there.
Oh, so poor Bilal has to move all the way there in this old and infirm age of his.
Enjoyed your lecture. I remember you gave one to stratigraphers a few years back in Turkey, and at that time I realized that your knowledge of the history of geology is incomparable, and that we have so much to learn from you. So I think those are my comments, basically, that your lecture today really put together for us. How do I describe it? A historical perspective that is, it is despairing from today.
Bilal, what you're trying to say is what Goethe had already said. Die Geschichte einer Wissenschaft ist die Wissenschaft selbst. The history of a science is the science itself.
Genau. Thank you.
Anke is right behind you.
Celâl, thank you very much. I would like to relay a question that is not my own question, and I would have not posed it that way because I know my own answer, but I think everybody else, and I know that you will enjoy to answer the question. So I do think that our distinguished colleague Paul Hoffman is not here, but he was the one who has raised the question. He's challenging you in giving Edward Suess all that much credit because he says that Edward Suess has not given due credit to the Precambrian, to the Proterozoic. So
because Paul is ignorant. He hasn't read what Edward Suess had written. The first chapter of Das Antlitz der Erde's third volume starts with the Precambrian. And Suess says this is what may have happened, but he says we don't have enough data to go into any more detail. Now, Paul, being a Canadian, he was born on the Precambrian, and at a time where we can date it, map it, analyze its rocks, so he's being unbelievably unfair and somewhat ignorant. So can you extend your answer also for your work on the Altaids? In what role does the Precambrian, the Proterozoic rocks play in your brilliant restoration of that? Very good point. Let me start by pointing out why my very good friend Dan Mackenzie has published 2 papers about the nature and formation of cratons. Being a good geophysicist, well, he started life as a physicist. He explained everything beautifully. But what he explained, what he described, doesn't look anything like the cratons. And the Altaid showed us that the reason why cratons like the Canadian Shield have vast, most of it, has a metamorphic grade at the surface between prehnite pompelliite and green schist at most. And the Altaids have the same thing. They have the same structure. They have the same sequence of events. And when I looked at places like Yilgarn, or the Barberton Mountain, or even Isua in Greenland, I went to the field in all those areas, and I was really flabbergasted about the similarity between the Altaids and these cratonic nuclei. And Altaids now is a cratonic nucleus forming in the middle of Asia. And if you leave it alone, thermally, for a long time, it's going to be a craton. And I think Kevin, in his preface to the Archean Greenstone Belts volume of Martin de Witt and Lou Ashwall, he wrote a short preface, but I would recommend anybody interested in the Precambrian to read it. And that's what Kevin pointed out.
So, thank you very much, Celâl. Some of you may have, I can see it looks like there's no more questions. So some of you may have wondered why we are not presenting the medal here, but the tradition is that the Union medals are presented during the award ceremony. So if you want to see Celâl receiving the medal, you should come here in this hall, I think it is tomorrow, late afternoon.
I was given a sneak preview. The way they arranged it this year, the big Union medalist, please translate or read as the old farts, will be there. And the younger medalists will be there. So they want us to appear together. So the younger generations will say, here is the past, here is the future.
So shall we give Celâl a hand?